So we'll continue. Our speaker is E Stein, and he will speak on some geometrical concepts arising in harmonic analysis.
Thank you. Very glad to speak at this symposium about the future of mathematics. I'd like to devote my talk to three parts. I'd like to talk a little bit about the past, a little bit about the present, and some speculations about the future. Yeah, so my subject is a connection which has in the past been worked out to be quite satisfactory between, on the one hand, certain central objects in harmonic analysis related to singular integrals, and on the other hand, certain kinds of geometry. I mean, something that a geometer probably won't call it geometry, but maybe an analyst will call it geometry, which is a notion of controlling distances, but only the order of magnitudes of distances. I'm going to speak more about that. Now, that has been quite a satisfactory system has been set up relating these two things. But now that we look at the thing more closely, we realize that there are some very serious issues which have to be analyzed, and I want to talk about those issues and something about speculation of what might happen in the future. So very quickly, the setting for the situation. We have here, these are singular integrals. I mean here a very, very general formulation. It's given by a kernel, which is singular somewhere, but I'll be more specific later. And some of the basic issues that have been considered are, of course, these arise in many applications. What I want to focus on is the kind of geometry that underlies these operators, which is a measurement, an approximate measurement of small distances. And this kind of measurement is crucial in describing the natures of the kernels of the operators and making all estimates of interest on these operators. And of course, related to this is how we prove estimates for these operators. So I'm going to start with a very quick review of some of this old stuff just to put the problem in its correct setting. Well, there's the classical theory, which is the Miquelin, Calderon, Zygmunt theory, etc. Let me just mention one feature of it. Here, the kernel k of xy is, let's say, taken on Euclidean Rn space, so it's Rn cross Rn. And it satisfies very characteristic differential inequalities. And the important thing to notice is this quantity, the norm of x minus y, which is, of course, the Euclidean distance. So here, the geometry is very, very simple. It's the obvious geometry. One doesn't even speak of geometry. But all the crucial estimates are in terms of this distance. And, of course, it's well known that under the appropriate conditions, which I don't give here because this is only a 45-minute talk, there is this L2 theory, and there's an LP theory, and there's a certain Calderon-Zygmunt paradigm, which is a well-known method of how to pass from L2 to LP inequalities. So this is a very old theory, and very quickly, why was it so important? Because it arose from various problems that have been mentioned. One of them is the study of the Hilbert transform of the Cauchy integral, which gives one very good example. I'm not going to be very specific. Another thing is in the theory of elliptic equations. If you take, say, a standard second-order elliptic operator and you look at a fundamental solution operator, and then you take the operator obtained by composing this with all the second partial derivatives, then you get one of these operators, one of these singular integral operators. And here the geometry, as I said, is the obvious Euclidean geometry. And all of this theory extends very quickly to a local theory, a localized theory on Riemannian manifolds where the distance is now taken to be the Riemannian distance. So that's the first very old picture of this theory, which I want to talk about. Now I want to come to also a pretty old extension of this theory, still very satisfactory, and I'm going to come to the unsatisfactory parts in a few moments. So this extension I can call the sub-Riemannian case, for it has been called, or can be called for lack of a better name. And there's a certain scheme in which you want to think about how this theory was developed. So the first step is Rn. That's, you might say, the classical theory that I just mentioned on Euclidean space. And then from Rn, we go to a situation where Rn is replaced by a nilpotent group with dilations. Dilations are one parameter family of automorphisms. When these groups were first studied from that point of view, they were called homogeneous or graded. Nowadays, they have another name. I think they're called Carnot groups. Anyway, that's, you might say, logically, you go from Rn to this more general situation. And then the next step from there is you go from this situation, which is a model situation, to a more general situation where you're talking about given a certain collection of vector fields which satisfy certain commutation properties, and you look at the geometry that is associated to that. So let me briefly describe this situation. I think probably the first occurrence arose in the theory of semi-simple groups of non-compact type. And here you have the standard Iwasawa decomposition. And then there's the group N, which is in some sense a boundary of the symmetric space G over K. Now that's the nilpotent group which arose, and the operators which arose were intertwining operators for certain unitary representations of these groups. And these turned out to be analogs of singular integrals, but associated to the group N. They arose naturally. And a very simple example of this was the group SUN plus 1, 1, where the group N then is the Heisenberg group, which is a very important example in all of this. And the symmetric space is the complex unit ball. And one of the very fundamental objects, which is the analog of the Cauchy integral, the Cauchy-Szego projection for holomorphic functions on the unit ball, turns out to be one of these intertwining operators. So that's one example. Let me very quickly mention two other examples of this still theory. So here the unit ball is replaced by some domain omega in Cn, which is strongly pseudoconvex. And now actually what one is looking at is the boundary of that domain, and the geometry, and this is an important point which I'm going to be describing more in a moment, is the so-called, is given by the distance, which is the control distance determined by certain vector fields. And vector fields are the vector fields that you obtain on the boundary, which are the real and imaginary parts of the tangential Cauchy-Riemann vector fields. I should stress that you can define this distance, and the exact distance will not be important. Only the order of magnitude of the distance, which will be important in all of these problems for us. So from the point of view of the analysis, what were the kinds of problems that could be solved and whose solution intimately involved this kind of geometry? Well, the Cauchy-Szego projection for these domains, and the solution and sharp estimates for the boundary D-bar complex, the box B, the so-called cone Laplacian. All of these were done by the use of this geometry. Now I give you a third example which arose in analysis. Of course, all of these problems come from analysis. It's when you're given a collection of x1 up to xk of real vector fields, smooth vector fields whose commutators span, and you form the sub-Laplacian associated with it, which is the sum of the squares. And then it turns out that, again, the control geometry, which is now associated to these vector fields, is the crucial geometry in terms of which all estimates are to be made. So, for example, if you write down what the solving operator is, or the relative solution modulo a small error, which is sometimes called parametrics, and you take the corresponding second derivatives with respect to the x's, you will get a singular integral with respect to this geometry. So now I'm going to say some words about this control geometry, or nowadays also called Carnot-Caratteodori geometry, because it is the crucial one. Now, so here is a quick discussion of the geometry which is associated to vector fields, or a geometry that can be associated to vector fields. So suppose we start with vector fields. This is meant to be x1. x1 up to xk are real smooth vector fields. They're just given locally. We don't assume that they span the tangent space at any point, but we assume that after taking finitely many commutators, they do. Now, then we define the distance between 2 points as follows. What we do is we try to go from point x to point y along a curve whose tangents here, whose tangents always lie along those given vector fields with coefficients such that normalize such that the sum of the squares is less than or equal to 1. Not only do we try to go along such points, but we try to see what is the least time that is involved to go from x to y, and that's the control distance. Now, it's a pretty remarkable fact that you can go from point x to a nearby point y if that condition of commutators is satisfied. And it's a fact that I guess was known implicitly for some time, but was first proved, I think, by Chow in around 1940. So what did Chow prove?
He proved for special cases. Karnov for simplicity proved it for.
Yeah. Okay. Well, I guess in this general form, he proved it.
About a couple of years earlier.
Mm-hmm. Well, okay. So now what we need for our analysis is a description of what this distance looks like, in particular what the balls of radius delta defined in terms of this distance looks like. Again, we need sort of an asymptotic description, not an exact description. That would be very hard to get and might be interesting for various other problems, but not for the problems of this kind. And now I mentioned this Calderon-Zygmunt paradigm, which is crucial sort of real variable method that could be used. And some of the conditions that are needed about these balls are stated here. The first condition is actually an easily verified condition. It's sort of an engulfing condition. And the second condition is what's called a doubling condition. It was pointed out by Kaufman and Weiss that this would lead to a general, whenever you have balls which have this property, you can have this paradigm apply very generally. All right, so this is what we need. Now I want to describe the geometry a little bit. So maybe I describe it over here. So I want to describe how one gets to this geometry, and one of the ways of getting to it is to model this geometry on certain free nilpotent Lie groups worked out by various people, and various alternate ways of doing things which are related. But basically, what one does is one starts with these vector fields, and then one forms strings of these commutators given by multi-index set I, and one assigns a weight or a degree to I, which is just the number of elements in that string of multi-commutators. And now we are lying in an n-dimensional space, so we form frames. Now a frame is any n-tuple of these multi-commutators, vector fields, and we assign a degree, which is just the sum of the degrees. And then we also assign the determinant of each frame, which is just the determinant. We have now n vectors in n-dimensional space, and that, of course, tells you the degree to which you have really genuinely linear independence. And now you form a function of delta. Delta is a parameter, a positive parameter. It's really a polynomial in delta, which encodes all of these numbers, which is the determinant of the frame times delta to the power, which is the degree of the frame. And this function, lambda sub x of delta, really determines, this polynomial determines the local geometry near x. I just want to say one or two words about how it determines the geometry, or what it tells you. It tells you what these balls look like. So for each x and delta, we choose that frame, and there may be several frames, and that's the whole point, that frame for which this polynomial, which in this sum gives essentially the maximum value. It's not uniquely determined, but any frame will do. And in that frame, the ball of radius delta, centered at the point x, looks like a box in the direction of these specialized vector fields of these specialized lengths, which is just determined by this. So very quickly, I'll just give you one quick example, just to give you a feeling for that. So here is the very simplest special case in R2, where you have two vector fields, x and y, which together with its commutator, which is ddy, spans. And you have two possibilities. You actually have to choose two sets of frames for each point. So typically, a point which lies on the singular axis, y equals 0, the boxes will look like having dimension delta in this direction and dimension delta squared in this direction. But when you're away from the axis, they will tend to look like having dimension delta and delta. And what's interesting is that as this point moves to this point, this kind of box merges to this box, but there's always the in-between region. And so you can never choose just one frame if you want to cover a whole area, which includes this singular line. All right. Now, the analytic consequences is that in this setup, there's a very satisfactory theory of singular integrals. So they are defined in terms of differential inequalities, where now you see in the denominator, you have this function v of xy, which is the volume of the ball which reaches from x to y, centered at x, which reaches to y. And then the differential inequalities are all in terms of distances from x to y. And you have operators which you could call of order m. The most interesting ones are of order m equals 0. And then the basic theorems are that if m is equal to 0, you get a bounded operator on L2 and on all the LP spaces. And these operators are, for example, the approximate inverses for the sub-Laplacian L and the kinds of operators that I mentioned before. So this is meant to give you a very, very quick, incomplete sketch of what I would call the sort of classical theory, and it's only that aspect of the classical theory of singular integrals which has a close connection with some kind of geometry, the geometry given by some distance function where all quantities are measured in terms of the distance function. And of course, all proofs actually the proofs can't be carried out without the use of that distance function. So that's a very, in some sense, extremely satisfactory picture. So what's the problem? Yeah. No, well, actually, the cancellation properties, which I passed over very quickly, because they're a little more complicated. No, they also can be expressed. Cancellation properties can be expressed in terms of defining what you might call bump functions, which are smooth functions which satisfy standard inequalities. and the action of these operators on these smooth functions. Now, these bump functions are themselves supported in balls, and the balls are given by this distance. And their differential inequalities are controlled by these vector fields, and so everything is within this geometry. So even the cancellation properties. The cancellation properties are also of that kind, but I didn't want to complicate the situation. So all of this is very satisfactory, except what is the problem? So now we come sort of to the present. This was all the past. The problem is this assignment of a theory, you might say, of singular integrals corresponding to a metric which is sort of naturally given by a problem. It turns out that there are many problems where there is not a unique metric underlying the situation. There may be two natural metrics that arise in the given problem. I'll give you some real examples of that. Two metrics which are not compatible. And then, in effect, when you're trying to analyze a problem, you have a choice of which of these two metrics you want to use. And the problem is that neither metric will now let you solve the problem. So with a little bit of patience, I'd like to describe two very specific examples. All right? So I want to call this the conflicts between two metrics. So let me explain how this arises. So in the first example, we're starting again with a domain now in Cn+1. Well, that's just slightly different. So this is going to be a problem in let's say, several complex variables, but also in PDE, as you will see in a moment. And we are looking, what we're really interested in is the boundary. Here's actually the picture of the domain. And we're interested in the manifold, which is the boundary of the domain. And now I'm going to say that there are two metrics. The first metric I just talked about, that's the control metric. So we take, again, the tangential Cauchy-Riemann vector fields, of which now there are 2n for the real and imaginary parts. And we take the control metric. So that's one notion of good, interesting notion of distance on the boundary. But there's another one, which for lack of better name, we call the zagometric. And that is determined also by the flatness, the complex flatness of this domain omega. Let me explain to you how it is. At least this metric can be defined if this omega happens to be convex of finite type. Finite type means that each point a tangent line makes at most a finite order of contact. That's a technical condition, but still, how do you define well, look at a point x. We want to define what are the balls centered at x of radius delta. We go in the normal direction by delta, and then we take the hyperplane perpendicular to the normal, and we cut off a cap. And that we would call the ball of radius delta. So that gives us a certain notion of a metric implicitly, and that's the zagometric. Now, unfortunately, the zagometric and you see the zagometric has a very natural reason for existing, because if you talk about the behavior of holomorphic functions inside this domain, in some sense the distance from the boundary should control a lot of things, and so that this metric should be play an important role, and indeed it does. So I want to just say a few things about the history of that metric. Well, here is a few things. Now I want to point out that when omega is strongly pseudo-convex, for example, a complex ball, then even though these two metrics are different, they are essentially equivalent because they give the same balls. The balls in one metric are merely a reparameterization of the balls in another metric. You change the radius of delta.
This metric isotropic, the one.
No. You're correct. That's the real case. There is a complex analog. I mean to talk about the complex analog. See, I'm trying to go fast because I'm trying to be within time, which I'm not going to be. There's a real case which was done first. Then there's a complex analog which was done by McNeil. And then there was the Cauchy-Szego kernel, which was studied. In the complex analog, you start to do the same thing, but you look at, first of all, the longest polydisk, complex polydisk in these directions. So it's a slightly different thing, but it has the same flavor. So, all right, it turns out that in the special case, where am I? I'm right here. In some special cases, they're the same, but in general, already, they're quite different. So here's a simple example. Of course, you can't do this theory without computing some examples. Here's a simple example, and here are the Cauchy-Riemann vector fields. And I'm just write down the order of magnitude of the distance function, one in terms of the control metric and one in terms of the Szego metric. The distance of a point Z1, Z2 from the origin for this example. And you can see from here that the metrics are inequivalent, but these formulas maybe don't tell you very much, so let me tell you what they really mean. The control metric assigns the same weights to the two complex tangential directions, Z1 and Z2. And then from that, it assigns a certain T direction, which is the missing direction in terms of the number of commutators you need. However, the Szego direction starts by calibrating everything in terms of the normal direction and then calibrates what the Z1 and Z2 direction should be. Now, why all of this fuss about these two metrics? Because there are three basic operators that you might want to consider in this thing. One is the Cauchy-Szego projection, and that turns out is controlled by exactly the Szego metric, and hence the terminology Szego metric. The other one is the sub-Laplacian, which is controlled by the control metric, so that. And the last one is the one which is the interesting one for the box B complex, and that's this box B operator. Here's an example of it. And it turns out that that box B operator is a second-order operator whose second-order term is L, but has certain other first-order terms which are very, very bothersome. And the right metric to control things is neither of these two, but seems to be a combination. So the question is, how do we understand, for example, the inverse of this operator? I mean, how do we make sharp estimates in this operator? If we try to work with one metric, we'd be lost because there's the influence of the other metric. So that's the problem. Now, very quickly, let me give you another example of this conflict, which is even simpler. This could have been the complex ball. I made it look a little more complicated. It's a domain in Cn+1, and there should be two metrics. And the two metrics are essentially, I'm writing down what the D-bar-Neumann problem is. It's like for the Laplacian, it's a complex version of the ordinary Neumann problem. Instead of taking the normal derivative and doing this, you take the complex, the Cauchy-Riemann vector field, whose real part is that normal derivative. And then you try to solve that problem, and that leads you to inverting a certain boundary problem. Now, why should there be two metrics? One metric comes from the underlying space and from the fact that you're dealing here with the Laplacian, which has the Euclidean metric, and so therefore you're taking the induced metric on the boundary, the induced metric coming from the Euclidean. It's a standard Riemannian metric on the boundary. And the other one is the control metric. Again, because you're in the complex space. So actually, how does this come out? When you compute what the operator is that you need to invert to solve this boundary value problem, lo and behold, there are certain computations and a lot of oversimplifications, but I will write down for you what this is. Well, this complex ball can be identified with the Heisenberg group, and you're led to a convolution operator with the Heisenberg group. And what you want to do is look at the kernel, which this convolution operator. And the kernel is a pointwise product of two kinds of singularities. One, this omega of z is meant to be a homogeneous function of degree 0 with a cancellation property. So that looks like the typical homogeneous Euclidean kind of singularity that you have in the classical theory of singular integrals in Rn. Actually, this is R2n plus 1. And here you have this kind of non-isotropic singularity, which goes with the Heisenberg structure or with the control metric. And you're looking to deal with an operator of this kind. And now, how does one deal with the operator? All right, so that is the problem. Now I'd like to come a little bit to the solution. Well, we don't really know the solution in general. We know it in these two cases. And there is a lot of speculation about what it might be in general, how we go about it. And I think what it involves is possibly interesting. So I would like to now discuss this with you, a little bit about the general philosophy of how we look at these two conflicting metrics and some speculation about it. How much time do I have left?
15.
Oh, okay. 15 minutes probably enough. Now, so let me explain what the setting is. So I'm going to describe, first of all, in the simplest situation, because as I say, we only understand this in very simple situation, what I want to call the two-factor case. You'll see why factors in a moment. So here, the way this sort of belief system that I want to describe for you, I won't quite call it religion, but call it belief system. So we start off, we are down here on our space M, and that is what we see, and we're trying to solve the problem on M. But what we don't see is up there is really a structure of a product of two M's and a certain projection. Okay, so that's what I'm going to try to explain to you, how this arises. And so the key words will be the notion of a lifting, which is to go from M to this M cross M1, M2, and there's the product. There's going to be a notion of flags that are associated to this, and of course there's the projection here. Now let me begin by trying to explain how this arises in some very special case, and then, as I said, I will speculate about what this might look like in the future. So now the way I want to go about this is remember, we went in the previous situation where we were sort of successful. We went from Rn to a model case, which is nilpotent groups with dilations, and then to a general situation. So I want to try the same steps, and we can be rather successful at the second step of nilpotent groups with dilations, but it's don't know yet what to do at all in general. So let's go back to this very special case which we had, where we were led to a certain convolution operator on the Heisenberg group with a kernel. And there again, I want to insist a little bit on the explicit, semi-explicit description of the kernel, just to make good sense of what all of this is. So you notice that this kernel has a singularity only at the origin, but that is when z is equal to t, that's the origin. It's a convolution operator. So as a kernel on the product space, of course, it's a singularity only on the diagonal. But here it's a convolution kernel, so it has a singularity at the origin. But the nature of its singularity is very complicated because it's got this thing which behaves in one way on the differentiations and this thing which behaves in an incompatible way. Now, it turns out that the right way to think of this is to consider this as being really a more singular operator than it is by introducing a virtual singularity. There's nothing fancy about this. We just knock out the t variable and assume that that's t variable over here. Just this t1 is not there, so that this becomes this. Now, why we do this is because it works. There are many other reasons to describe it. I'm not going to go into the motivation. But we can now consider operators of this kind which look more singular. But now here we come to the very crucial thing of what we've done. We have taken the ZT space, And we originally had a singularity only at the origin, which is this blue point here, which is the standard kind of thing one has in singular integrals. And we've introduced a whole new singularity because this factor is singular when z is equal to 0. So we have this region, and this region with t, 0t happens to be a subgroup. We have a whole subgroup, and so we now want to thought, and this is a very special example of a flag kernel. So what is the flag here? Here it's the origin, and then it's the subgroup S, and then it's the full group Hn. And what is really happening is that this flag describes the nature of the singularities of the kernel K, first in a very generalized sort of way, but then if you think about it, you can write down very specific kinds of inequalities that should be satisfied. So the kernel is most singular at the origin, that's over here, and then going up here in this flag, it still has singularities, but of a weaker kind along here, and then of course on the rest it is regular, and then it satisfies the appropriate differential inequalities, and of course you have to guess what they are, for this flag, together with the appropriate cancellation conditions. Yes?
Are the L2 issues also problems in this already?
Oh yeah. That main problem is to prove that such an operator is bounded on L2, and to know what. So all of these problems are mixed together, but even to understand what kind of operators you're dealing with, you have to. This is what I'm talking about, but that's really what you want to do. So for a long time, it wasn't known what class of operators these are. But so this turns out to be the notion. So this is the first point is that this is the way you want to consider this operator. Now, how do you consider this operator? Okay, suppose you say you want to consider operators which allow such singularities. What do you do to consider this operator? Now it turns out that the only way we see how to consider this operator is not to stick in the ZT space, but to go to a higher space and then deduce the results from a higher space. So that's what all that lifting and projection was all about. So let me now state what is going to go on. All of these steps require quite a bit of work, and I'm just going to say what they are. So we start over here with a operator, a kernel on the Heisenberg group Hn, and now we think of Hn, of the product of Hn cross R, that's M1 cross M2, projected to Hn, where Hn is Z comma T and R is U, and this is the projection. So Hn is really the quotient of the product times that subgroup. And what we do is we start with our kernel K, which is the one up here, not necessarily that one, but the one up here, and we lift it in a certain way to a kernel on the product group. That's the first way, in such a way that this new kernel is a product kernel. Now, what do I mean by a product kernel? This is also a long story, but what we mean is that once we have a product of two things, we can think of, first of all, kernels which act just on one variable, tensor product kernels which act on the other variable. That's the simplest kind of product kernel. But the general product kernel will be, in some sense, a limit of linear combinations of these in the converging in the appropriate sense. That will be the product kernel. So a product kernel will satisfy product inequalities. So the first thing is to lift this kernel, and it's not completely trivial, to 1 in the higher space so that it becomes a product kernel, so that the product theory applies to that. And from the product theory, we can then prove, let's say, the boundedness on L2 or the boundedness on LP, and then to project backwards. And the projection is just an integration over this gamma. And there's the integration. So that is how we would obtain the L2 and the LP inequalities. All right. So that's the general scheme of how we would do it in this case. And this scheme can be generalized, at least in the case of nilpotent groups with dilations, to when you have flags of a very special nature, which are an increasing family of subgroups which themselves are homogeneous, that is, under these dilations, and satisfy a certain extra condition which I state in terms of the Lie algebras. But actually what it means is that there is another group, n tilde, such that if n arises from n tilde as a homomorphism, and such that the Sj's are the homomorphic image of just the product of the first Nj's. That's the basic idea. Now, in that case, one can do all of this machinery. So I just want to say that in the special case of Hn, which I mentioned before, this was done a few years ago, and now in this more general case, it's been done recently, not yet published. All right, so that takes care, so to speak, of one of the examples. Now, very, very quickly, let me just say, how much time? I have no time left. No? Oh, 8 minutes. Well, I will take less than 8 minutes. Let me just say, in the second example, you see where our domain arose as follows. We took, in 3 complex variables, the domain omega, which was the imaginary part of little omega being bigger than phi1 of z1 plus phi2 of z2, where phi1 and phi2 were 2 specific functions. But this is more general. Now we can consider 2 separate domains in C2, their boundaries, and consider this product, and in a natural way we get a projection. And the theory for this domain turns out to be the one that you would get from the product theory, and then you can define the notion of flags. Here now the notion of a flag would be that for each point x, you would get an appropriate submanifold passing through x of fixed dimension, which varies, of course. This submanifold would vary nicely with x. In this case, it would be a simple example of a flag, and you'd have appropriate notions of flag kernels. And in this particular case, you can do a similar theory. It has not yet been written down fully. I now want to come to the very end of my talk, which is the main question of what is the general theory to look like? So these are just questions. So what is the general theory that we can look, that we could hope, which is modeled a little bit along the lines of the theory that I had just sketched before for homogeneous groups. And so what can we expect? Well, first of all, the underlying geometric structure will be a flag of submanifolds given for each point x of, let's say, length L, where L is fixed. And associated with these will be a corresponding increasing family of vector fields. And so that the Lth collection, the full collection, consists of starting with certain vector fields x1 to xk, and then all their commutators of length m. That will be the underlying data. And now, then one will, again, this is all very vague because we don't know exactly how to state this. So it's my last few minutes. I'm allowed to be vague. So yeah, what we want to do here is consider a family of operators. These are going to be our singular integral operators. And these operators are going to have singularities when when y rather, lies in the flag based at x. But the degree of singularity will depend on the j. So when j is equal to 0, which is the point x, we will have the heaviest singularity. Then we'll have another singularity not as heavy at j equals 1. And finally, at j equals L, it'll be regular. So that will be part of what's given. And now, that should be the way the thing looks. And here now, what are the problems? So the first problem is to know exactly how to state the geometric conditions that we want to require of these flags and these collection of vector fields. Well, of course, one of the natural conditions to require is that the collection gamma k span the tangent space for the submanifold V upper K. But presumably there are some other geometric conditions which we don't understand. And then we want to understand what are the precise differential inequalities on these kernels, which will of course be determined by these vector fields and distances in some sense from these submanifolds. And then, of course, once we understand that, of course, part of understanding that is how to prove anything about these operators, how to prove that they're bounded, and why do they form an algebra. Presumably they form an algebra. Now, the last thing I want to leave you with is that there is probably a hint to all of that, because a very special case of this, I would think probably, has been done. And that is when you have the flag consists of just one manifold, which is given this way as the in terms of the exponential function, and these are the so-called singular Radon transforms. So in this case, what you have is that the kernel happens to be entirely supported on the subvariety. So there are no differential inequalities here. Everything is on the subvariety, and of course there you then have to formulate what these cancellation conditions are. But here we know the theory, and this should be a special case of the general theory. And of course, as I tried to indicate, that this class of operators would seem to have connections with many problems in PDE and several complex variables, and so they may be of interest for further study. So that's it.
Questions, please. Do you see any intrinsic possibilities for direct geometric approach without the lifting of lines, covering them?
No, not right now. No, not right now. It looks no. It's a very good question.
Even for the Radon case?
Yeah, right. It looks, yeah.
More questions? Actually, according to our schedule, so it can start with questions, the other questions.